Welcome to LIB Academy, and this is our third video in the playlist Quantum Mechanics. We are going to look at linear operators and non-linear operators. Already we knew what operators are. Operators are mathematical identities that tell us to do something, right? Example is the plus sign, the addition sign, the derivative sign. All those are example of operators, and we do have operators in quantum mechanics too. We already thought about that. I mean, we already dealt with those operators in the previous video. You can check them out, or basically that's what operators are. So our point of interest here is whether to tell whether an operator is linear or non-linear. And an operator is said to be linear when it obeys the additivity. This law, let's say we have our operator O. For this to be a linear operator, if we operate O on the function f of x plus mu, this is mu, g of x, it should give us gamma, the operator, and the function f of x plus mu and the operator and the function g of x, where the gamma here, gamma and mu here are arbitrary numbers. They can either be complex or real numbers. So this is a general equation. I'm going to simplify this. These ones are indicating sometimes the function might have a coefficient, right? So let me just simplify this. So this is just to say if we have the operator O operating on the function f of x plus the function g of x, it will give us this operator multiplying the function f of x plus the same operator multiplying the function g of x. So for an operator to be linear, it should obey this formula. That is one of the formula that you should obey if indeed it is a linear operator. We'll look at examples very soon. And another equation you should also obey is, let's say, if the operator operates on a function with f of x, it should give us the operator and the function f of x. So this is it should obey homogeneity, and this is the additivity, right? You can basically see that we are just expanding this at the end. If you operate this on these functions, into bracket these functions, the results will be the operator operating on each of the function. I mean, it should be the sum of the operator operating on each of the function, let's say f of x and g of x. So an operator is said to be a linear operator if it obeys these two equations. So I think these two equations are simple to put in mind as compared to the first one, right? So let's look at examples of operators, I mean linear operators and non-linear operators. And after that, we then look at why operators. Why do we have to look at linear operators and non-linear operators in quantum mechanics? Examples of linear operators that are linear are the derivative, differentiation, Differentiation is linear. Integration, matrix multiplication. I mean, matrix multiplication, which is linear algebra, as the name suggests. Linear algebra. Example, let's see whether the operator d over dx squared is linear with the given functions f of x and g of x. Let's see whether it is linear. So how do we do that? We recall our formula. That operator operated on f of s, the sum of f of s and g of x. So our operator is d over dx. So it should operate, squared. It should operate on, let's say, the sum of the two functions, which is f of x and g of x, to give us the same operator, d squared over dx squared, f of x plus d over dx squared, g of x. And we can actually see that this and that are the same, right? It's just the same. So what you have to know is that differentiation, integration, and matrix multiplication are linear, right? And we'll be using this in our quantum mechanics journey. Let's look at this example. What of square root of 9 plus 16? Is it not the same as square root of 25? Because 9 plus 16 is giving us 25. So this is going to give us 5, right? So in this case, this is our operator. The square root sign is our operator. And let's assume this is our functions. These are our functions, 9 and 16. So our operator is now operating on 9 and 16. So this gives us 5, right? What if we take the square root of 9 plus square root of 16? What do we get? Basically, this is going to give us 7, right? Because this gives us 3, this gives us 4, 7. And you can see that 5 is not equal to 7. So the square root sign is a non-linear operator. Another way to prove, let's say, if it is a linear operator, then let's say this is our operator, right? This is our operator. Unlike here, we have our operator outside. You see, let's say the square root sign now is now our operator, and our function are f of x. Our functions are f of x and g of x. So let's say 9 plus 16, right? It should be equal to our operator plus the one of the function plus our operator plus the remaining function, right? So you can see that this, a whole of this will give us 5, right? But a whole of this will give us what? 3. This will give us what? 4, which is 7. And 5 is never equal to 7. So this means that square root is an example of non-linear operator. So let's now look at examples of non-linear operators. The square root sign is an example of non-linear operator. The trig functions, sine, cos, are all non-linear operators. Exponential are non-linear operators. Squares, cubes, are all non-linear operators. So now let's look at our point. What interests us is here. We in quantum mechanics will be dealing with linear operators, right? It appears that nature is adequately described by this class of operators. So linear operators are very important in our journey of quantum mechanics. That is it for this video. See you in the next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye. Feel free to support this channel by liking and subscribing. Thank you.